Tonight, we are going to take a journey together, a quiet journey through space and time, a journey that will gently shift the way you see your place in this vast cosmos. We are going to explore the true scale of the universe and discover, in the most peaceful way possible, just how small Earth really is, not small in comparison to a mountain or an ocean. Not even small compared to the sun alone, but small in a way that makes our entire world almost vanish when placed in its proper context. By the end of this journey, as you drift towards sleep, the planet beneath you may feel very different from the way it does right now. Before we begin, if you find comfort in these explorations of space and our cosmic perspective, a gentle like or subscribe would help this channel continue creating these peaceful journeys. It is a small gesture, but it makes a real difference. Now let us begin. Let us start where we are, right here, right now on Earth, our home. From the surface, standing where you are at this very moment, Earth feels immense, limitless, even. You could spend an entire lifetime traveling across its continents and still not see every corner. The oceans stretch for thousands of miles in every direction, covering more than 70% of the surface. Mountain ranges rise high enough to pierce the clouds. Cities expand far beyond what the eye can see from any single vantage point. To early civilizations, Earth was everything. The entire universe existed on this ground beneath their feet. The sky above appeared like a dome, a ceiling painted with distant lights. The land beneath seemed flat and endless. The stars were just that, lights. Fixed to the celestial sphere, revolving around us as the center of all creation, this worldview made perfect sense. It matched human perception. When you stand at the horizon and look out across the land, the curve of the planet is too subtle to detect. Earth appears stable, central, vast. It feels like the foundation of reality itself. And in a very real way, it is, for us. Earth has a diameter of roughly 7,926 miles at the equator. If you could somehow walk in a straight line around the equator, maintaining a steady pace of 3 miles per hour for 8 hours each day, it would take you more than 3 years to complete the journey. 3 years of continuous walking just to circle once around this world. Its total surface area measures about 197 million square miles. If you visited 1 square mile every second without stopping, it would still take over 6 years to see the entire surface. 6 years, every second, just to glimpse every part of this planet. By human standards, Earth is enormous. It is a world large enough to contain every landscape we have ever known, every civilization that has ever existed, every story that has ever been told, every dream that has ever been dreamed. Every person who has ever lived has walked on this world, breathed this air, looked up at this sky. The United States, one of the largest countries, covers only about 3.8 million square miles. That is less than 2% of Earth's total surface. Russia, the largest country by area, spans about 6.6 million square miles, still only about 3% of the planet's surface. China covers roughly the same area. Canada, Brazil, Australia, each vast in their own right, together occupy only a fraction of Earth's total surface. To frame this magnitude in another way, if you wanted to visit every square mile of Earth and spent just 1 second in each location, it would take you over 6 years of continuous travel. No sleeping, no resting, no pausing for even a moment. 6 years to touch every corner of this world. The deepest ocean trenches plunge nearly 7 miles below the surface. Mount Everest rises nearly 6 miles above sea level. The distance from the deepest point on Earth to the highest is about 12 miles. 12 miles of vertical relief on a world that measures nearly 8,000 miles across. The atmosphere that surrounds us extends upward for hundreds of miles, gradually thinning until it merges with the vacuum of space. But most of the air we breathe, most of the weather we experience, exists in just the lowest 6 miles of atmosphere, a thin skin clinging to the surface of our planet. But the sense of magnitude begins to shift the moment we move beyond the surface. When astronauts look back at Earth from orbit, something changes. The continents no longer appear endless. The oceans no longer seem infinite. From just a few hundred miles above the surface, our world becomes a sphere, a complete object, whole and finite. You can see the curvature. The thin blue line of atmosphere clinging to the surface, the fragility of it all. Rise a little farther, and Earth becomes a marble suspended in darkness. Continue outward to the distance of the moon, and it shrinks into a small blue disk. Eventually, at sufficient distance, it becomes a pale point of light, indistinguishable from the surrounding stars. A tiny dot in an ocean of black, the physical size of Earth has not changed. Its diameter remains 7,926 miles. Its surface area remains 197 million square miles, but its apparent importance has shifted. It is no longer everything. It is one thing, one object, among countless others. This is the beginning of understanding, the beginning of perspective, the beginning of seeing Earth not as the center of all existence, but as one small world, orbiting one star, in one galaxy. Among trillions, and we have only just begun to zoom out. The journey ahead will take us farther than most people ever contemplate. We will leave Earth behind. We will pass the moon. We will travel beyond the sun, beyond the solar system, beyond the stars we can see with our naked eyes, beyond our galaxy, beyond clusters of galaxies, to the very edge of what we can observe. And at each step, Earth will shrink, not physically, but in significance, in apparent size, in the role it plays in the cosmic story. By the end, you will understand something profound. Something that might change the way you see your own life, your own struggles, your own place in this vast, ancient, beautiful cosmos. So settle in, relax. Let your mind wander through the darkness of space. Let the enormity of it all wash over you gently. There is no rush, no urgency, just a slow, steady journey outward, into the infinite. Let us continue our journey. Let us step away from Earth and look at our nearest companion in space. Now let us turn our attention to our nearest neighbor, the Moon. The Moon orbits Earth at an average distance of about 238,855 miles. That distance is difficult to picture at first. But here is one way to understand it. You could line up roughly 30 Earths in a straight line between our planet and the Moon, 30 entire worlds. Each one as vast as the planet beneath your feet right now. All of them could fit in the empty gap separating us from the object that dominates our night sky. Think about that for a moment. The Moon, which appears so close when you look up at night, is actually separated from us by a distance equal to 30 Earths placed side by side. That is an enormous amount of empty space. Cold. Dark, silent. When we see images of Earth and the Moon together, they are often shown much closer than they truly are. Artistic renderings compress the distance to fit both objects in frame. It makes for a more pleasing image, but in reality, this nearby region of space is filled mostly with emptiness. When Apollo astronauts traveled to the Moon in the late 1960s and early 1970s, it took them about 3 days to make the journey. 3 days of traveling at speeds exceeding 24,000 miles per hour, just to cross the gap between Earth and its nearest companion. The Moon itself has a diameter of about 2,159 miles, roughly 27% the size of Earth. If Earth were the size of a basketball, the Moon would be about the size of a tennis ball. That may seem modest, but our Moon is actually unusually large relative to its planet. In many other planetary systems throughout the cosmos, moons are tiny compared to the worlds they orbit. Jupiter's smallest moons are just a few miles across. Saturn has dozens of moonlets barely large enough to be called objects, mere fragments of rock and ice held in orbit by the planet's gravity, but Earth's moon is substantial, significant. It is the 5th largest moon in the entire solar system. Only Jupiter's Ganymede, Saturn's Titan, Jupiter's Callisto, and Jupiter's Io are larger. And those are moons orbiting planets far more massive than Earth. The Earth-Moon relationship is unique enough that some astronomers describe it as a double planet system. We do not simply have a moon orbiting us, we have a companion, a partner in our journey through space. The Moon influences Earth in profound ways. It creates the tides that shape our coastlines. Twice each day, the oceans rise and fall in response to the Moon's gravitational pull. This rhythm has existed for billions of years, long before there were humans to observe it. Long before there was any life at all. The tides are caused by the difference in gravitational pull across Earth's diameter. The side of Earth facing the moon experiences slightly stronger gravity than the center. The side facing away experiences slightly weaker gravity. This difference creates bulges in the oceans. As Earth rotates, these bulges sweep around the planet, creating the rising and falling tides we observe. The moon also helps stabilize Earth's axial tilt. Our planet lanes at an angle of about 23.5 degrees relative to the plane of its orbit around the sun. This tilt gives us our seasons: summer and winter, spring and fall. The gentle cycle of warmth and cold that makes our world habitable and predictable. Without the moon's stabilizing influence, Earth's tilt could vary wildly over millions of years. Computer simulations show that without the moon, Earth's tilt could swing anywhere from 0 degrees to 85 degrees over geological timescales. The climate would become chaotic, unpredictable. Life, particularly complex life, would struggle to adapt to such dramatic shifts. The moon, in its quiet way, helps make Earth the stable home we know. It has been doing this for over 4 billion years, silently, patiently, a guardian of stability. The moon is also slowly drifting away from Earth. Each year, it moves about 1.5 inches farther away. This happens because of tidal interactions between the two bodies. The same gravitational forces that create ocean tides also transfer rotational energy from Earth to the moon's orbit, very slowly, very gradually. Billions of years ago, the moon was much closer to Earth, so close that it would have appeared enormous in the sky, perhaps 3 or 4 times larger than it looks today. Days were shorter back then. Earth rotated much faster. A single day might have lasted only 5 or 6 hours. The moon's gravitational pull has been slowing Earth's rotation ever since. As Earth slows, the moon drifts outward. This exchange of energy will continue for billions of years to come. Eventually, Earth and moon will become tidally locked to each other. Earth will show the same face to the moon at all times, just as the moon already shows only one face to us. But that is so far in the future that it becomes almost meaningless to contemplate. Long before then, the sun itself will have changed, aged, swollen into a red giant. For now, the moon remains our closest companion in space, a familiar presence in our night sky. Every culture in human history has looked up at the moon, named it, told stories about it, worshipped it, measured time by its phases. The moon's surface is scarred by billions of years of impacts. Craters of all sizes cover its face. Some are hundreds of miles across, others are just a few feet. Each one tells a story of a collision. A rock or asteroid that ended its journey by slamming into the moon at thousands of miles per hour. The moon has no atmosphere to burn up incoming objects, no weather to erode the craters over time. So they remain preserved, a record of 4.5 billion years of cosmic bombardment. The dark patches we see on the moon are called maria, Latin for seas. Early astronomers thought they might be actual bodies of water, but they are not. They are vast plains of solidified lava. Billions of years ago, massive impacts cracked the moon's crust. Molten rock from the interior flowed out, filling the impact basins. When it cooled, it created the dark, smooth plains we see today. The moon is the only other world that humans have ever walked upon. Between 1969 and 1972, 12 astronauts stood on its surface. They collected rocks, planted flags, took photographs, left footprints that will remain undisturbed for millions of years in the airless, weatherless lunar environment. And yet, even this significant companion, even this world we have touched with human hands, is just one small object in a much larger cosmic neighborhood. Let us continue outward. Let us turn our gaze toward the sun. Now let us turn our attention to the sun, the star that makes life on Earth possible. The great engine of warmth and light that has shaped our world for billions of years. From Earth, the sun appears large and dominant in the sky. It feels close, personal. It rises and sets with comforting regularity, marking the passage of days and seasons. But when we step back and look at the sun in cosmic terms, we see something different. we see a star among stars. Powerful beyond imagination, yet still only one small point of light in a vast and mostly dark universe. The Sun has a diameter of about 864,000 miles. That is 109 times wider than Earth. If Earth were the size of a basketball, the Sun would be about 10 feet across. If Earth were a peppercorn, the Sun would be about 10 feet across. Either way, the difference in scale is staggering. The Sun's volume is so immense that more than 1.3 million Earth-sized spheres could fit inside it. Every mountain, every ocean, every city, every person who has ever lived, every part of Earth could be replicated more than 1 million times within the Sun's interior. And yet, compared to some other stars, the Sun is average, ordinary, a yellow dwarf, as astronomers call it, a common star in a common galaxy. The Sun's energy comes from nuclear fusion. Deep in its core, hydrogen atoms are squeezed together under immense pressure and heat. They fuse into helium, releasing enormous amounts of energy in the process. Every second, the Sun converts about 600 million tons of hydrogen into helium. This energy then travels outward through the Sun's layers, eventually reaching its surface and streaming into space as light and heat. That light takes time to reach us. Light travels at 186,000 miles per second. Even at that incredible speed, sunlight takes more than 8 minutes to cross the 93 million miles from the Sun to Earth. If the Sun were to vanish right now, we would not know for over 8 minutes. The last rays of sunlight would continue their journey toward us, and Earth would still be bathed in light until that final wave arrived. This is a gentle reminder of the vastness of space. The Sun feels immediate to us, but it is not. It is distant. Its influence reaches us across millions of miles of emptiness, and even then, the light we see is already old by the time it arrives. The Sun's surface, the layer we see, has a temperature of about 10,000 degrees Fahrenheit, but the core is far hotter, about 27 million degrees Fahrenheit. The pressure at the core is about 260 billion times Earth's atmospheric pressure. Under those conditions, matter behaves in ways that are hard for our everyday intuition to grasp. Electrons are stripped away from atoms. The material becomes a glowing plasma, a fourth state of matter where charged particles move freely. From the surface, the Sun often shows us dramatic activity. Sunspots appear as darker regions where magnetic fields suppress the flow of heat from below. Solar flares erupt, releasing enormous bursts of radiation. Coronal mass ejections hurl billions of tons of charged particles into space. When these particles reach Earth, they can interact with our magnetic field, producing the beautiful auroras near the poles. They can also disrupt satellites, power grids, and communication systems. The Sun is not a perfectly calm, steady source of light. It is dynamic, alive with magnetic forces and energy. It changes over days, weeks, and years in cycles that scientists have studied for centuries. Understanding these cycles helps us predict space weather and protect our technology. But for most of us, the Sun's variability is subtle. It rises, it sets, it warms the day, it cools the night. Its light nourishes plants and fuels the weather systems that shape our world. The Sun is the engine of Earth's climate. It drives the water cycle. It powers photosynthesis, the process by which plants convert sunlight into chemical energy. Without the Sun, Earth would be a frozen, lifeless world, a dark rock drifting through space. Looking at the Sun from Earth also gives us perspective on Earth's place in the solar system. Earth sits at what astronomers call the habitable zone, the region around a star where liquid water could exist on a planet's surface. Too close to the Sun, and water would boil away. Too far and it would freeze solid. Earth sits in that narrow band where liquid water is possible, where life as we know it can thrive. This is not a coincidence. It is the result of many factors working together. Earth's distance from the Sun, its atmosphere, its magnetic field, its size and mass, its water content, its long-term stability. All of these things combine to create a world where life can persist and evolve. The Sun, in this sense, is not just a source of light. It is the foundation of Earth's habitability. It is the reason we have weather, seasons, and the energy that supports every ecosystem on the planet. From the smallest microbe in the ocean to the largest whale, from the tiniest blade of grass to the tallest tree, all life on Earth depends on the sun. And yet, when we step back and compare Earth to the sun, Earth becomes almost laughably small. The sun is a star. Earth is a planet orbiting it. The sun contains 99.86% of all the mass in the solar system. Everything else, planets, moons, asteroids, comets, makes up just 0.14%. Earth is a tiny fraction of that already tiny remainder. This perspective can feel humbling, even frightening. It can make us feel insignificant in the face of cosmic forces so much larger than ourselves, but it can also be deeply comforting. Because it reminds us that we are part of something vast and ancient. We are living on a small world warmed by a great star, in a universe that stretches far beyond our imagination. As we continue our journey outward, we will see the sun shrink. It will become just one star among billions. Earth will shrink with it, until it becomes, once again, a pale blue dot suspended in the darkness. But for now, let us remain here for a moment longer. Let us feel the warmth of the sun on our faces. Let us appreciate the light that makes life possible. Let us recognize that our small world, fragile as it is also extraordinary. Because in all the vastness of space, we know of only one place where life exists, and that place is here, on this tiny planet orbiting an ordinary star. Take a slow breath. Let the scale of it all settle into your mind, not as a source of fear, but as a source of wonder. The sun is enormous, Earth is small. In life, consciousness, awareness, these are rare and precious things in the cosmic dark. Let us drift outward now, from the sun to the other planets, from our solar system to the stars beyond, and from there to the vast structures that make up the universe itself. Now that we have felt the scale of the sun and understood how it governs our world, let us drift outward a little farther. Let us visit Earth's closest neighbors, the inner planets, Mercury, Venus, and Mars. These worlds are not distant abstractions. They are part of our immediate cosmic neighborhood. And each one tells a different story about what a planet can become. We begin closest to the sun. Mercury is the innermost planet, orbiting at an average distance of about 36 million miles from the sun. That is only about 38% of Earth's distance from our star. Mercury's year is short. It completes an orbit in just 88 Earth days, but a day on Mercury is long, very long. Mercury rotates so slowly that one full day, from sunrise to sunrise, lasts about 176 Earth days. That means on Mercury, a single day is longer than 2 of its years. Mercury's environment is extreme. With almost no atmosphere to hold in heat, temperatures swing dramatically. In direct sunlight, the surface can reach about 800 degrees Fahrenheit. In the darkness, temperatures can plunge to about -290 degrees Fahrenheit. There is no gentle moderation of climate. No thick blanket of air to soften the contrast between day and night. Mercury lives in extremes. Its surface is heavily cratered, a record of billions of years of impacts. Without weather to erode the landscape, those craters remain almost unchanged. Standing on Mercury would be like standing on a world frozen in time, ancient scars preserved with almost no alteration. The planet's largest crater, the Caloris Basin, stretches about 930 miles across, an enormous wound in the surface, a reminder of the violent history of the early solar system. Mercury is small, about 38% of Earth's diameter. If Earth were a basketball, Mercury would be about the size of a golf ball, yet Mercury is dense. Its iron core makes up a large fraction of its mass. Scientists believe Mercury's core is unusually large, perhaps because ancient collisions stripped away much of its outer mantle. Even a small world can hold deep mysteries. As we drift outward, we come to Venus. Venus is often called Earth's twin because of its similar size. It has a diameter of about 7,521 miles, about 95% of Earth's diameter. But that similarity ends quickly. Venus is not a welcoming twin. It is a world transformed into something almost alien. Venus's atmosphere is overwhelmingly carbon dioxide, with thick clouds of sulfuric acid. The atmospheric pressure at the surface is about 90 times that of Earth. Standing on Venus would be like standing nearly 3,000 feet underwater on Earth. The pressure is crushing. And the heat is relentless. The average surface temperature on Venus is about 900 degrees Fahrenheit, hot enough to melt lead. This is not just because Venus is closer to the Sun. It is because of a runaway greenhouse effect. The thick atmosphere traps heat with extraordinary efficiency. The sun's energy pours in, and very little escapes back into space. Venus is a world where the greenhouse effect has run completely out of control. Venus also rotates unusually slowly and in the opposite direction from most planets. One day on Venus lasts about 243 Earth days. The sun rises in the west and sets in the east. No one knows for certain why Venus rotates this way. A massive impact early in its history may have reversed its spin, or complex interactions between the atmosphere and the planet's rotation may have caused the change over time. Despite the harsh conditions, Venus has fascinated scientists for centuries. Its brightness in the night sky made it one of the first planets to be recognized as a world distinct from the stars. Its thick clouds reflect a large amount of sunlight, making it the brightest planet visible from Earth. As we leave Venus behind, we feel the temperature drop. We move farther from the sun. And we approach the next world on our journey, Mars. Mars is the fourth planet from the Sun, about 141 million miles away. About 1.5 times Earth's distance from the Sun, Mars is smaller than Earth, with a diameter of about 4,212 miles. About 53% of Earth's diameter. About 7 Mars-sized planets could fit inside Earth. Mars is a cold desert world. The average temperature is about -80 degrees Fahrenheit. It can get warmer near the equator, occasionally reaching above freezing, but for the most part, Mars is frozen. Mars has a thin atmosphere, mostly carbon dioxide, with surface pressure less than 1% of Earth's. That thin atmosphere cannot hold in heat the way Earth's does. It cannot support liquid water on the surface for long, and so Mars is dry. Its rivers and lakes are gone, leaving behind only their traces, but those traces are everywhere, ancient river valleys. Lake beds, mineral deposits that form only in the presence of water. Mars was not always the cold desert it is today. Billions of years ago, Mars had liquid water on its surface. It may have had a thicker atmosphere. It may have had a more temperate climate. It may even have been a place where life could have existed. Today, Mars preserves the evidence of that wetter past. The rovers we have sent there have found minerals that form in water. They have found sedimentary rocks that look like they were laid down in ancient lakes and rivers. They have found evidence of groundwater. Mars is a world that once held water, and that fact makes it one of the most important places in our solar system for understanding the potential for life beyond Earth. Mars has 2 small moons, Phobos and Deimos. Phobos is only about 14 miles across. It orbits so close to Mars that it goes around the planet 3 times each Martian day. Phobos is slowly spiraling inward. In about 50 million years, it will either crash into Mars or break apart, forming a ring around the planet. Deimos is even smaller, about 7.5 miles across. It orbits farther out and is less affected by Mars's gravity. Standing on Mars, the sky is a pale pink color, tinted by dust in the atmosphere. The sunsets can be spectacular, with the sky glowing in shades of blue, purple, and gold. The landscape is stark and beautiful. Vast plains, towering volcanoes, deep canyons, a world that feels ancient and quiet. Mars is close enough that humans may one day visit it. Someday perhaps even settle there, but it is not a place where life will be easy. The thin atmosphere offers little protection from radiation. The cold is relentless. Water is scarce. Yet Mars remains one of the most compelling worlds in our solar system, a place where the past of water and the possibility of life linger in the rocks and minerals beneath our feet. As we leave Mars behind, we begin to see something important. The inner solar system is a set of worlds shaped by the sun's influence. Each planet tells a different story. Mercury scorched and cratered, Venus trapped in a runaway greenhouse, Earth balanced and alive, Mars once wet now frozen, 4 worlds, 4 outcomes, all governed by the same star. And beyond Mars lies a much larger realm, the outer solar system, the gas giants, the icy worlds, the vast distances between them. The scale of it all is about to grow again. And Earth, already small, will shrink still further. Let us drift onward. Let us move beyond the inner planets into the wider solar system. Let us see how small Earth becomes when compared to the giants that lie beyond. Between Mars and the next planet lies a vast gap, a region filled with countless rocky fragments. This is the asteroid belt, a zone stretching from about 220 million miles from the Sun to about 330 million miles out. The asteroid belt contains millions of objects, rocky remnants from the early solar system, material that never quite came together to form a planet. Perhaps Jupiter's powerful gravity disrupted the formation process, scattering the material instead of allowing it to coalesce. Despite containing millions of asteroids, the belt is mostly empty space. The distances between individual asteroids are enormous. If you flew a spacecraft through the asteroid belt, you would likely see nothing at all with the naked eye. The asteroids would be too far apart, too small, too scattered to notice. The reality is nothing like the crowded fields of tumbling rocks portrayed in movies. The largest object in the asteroid belt is Ceres, a dwarf planet about 588 miles in diameter. That is only about 7% of Earth's diameter. Ceres is round, shaped by its own gravity, and scientists believe it may have a subsurface ocean beneath its icy crust. Even in this debris field, there are worlds with their own mysteries. Most asteroids are far smaller. Vesta, the second largest, is about 326 miles across. Most asteroids are just a few miles or even a few hundred feet in diameter. Fragments of rock and metal drifting silently through space. As we leave the asteroid belt behind, we cross an invisible boundary. We move from the realm of rocky planets to the realm of giants. The outer solar system, where the planets are not made of rock but of gas and ice, where the distances become so vast that our familiar sense of scale begins to fail. We arrive first at Jupiter. Jupiter dominates the outer solar system like no other planet. It is enormous, massive, the king of worlds. Jupiter has a diameter of about 86,881 miles. That is about 11 times wider than Earth, but volume is what truly matters. Jupiter's interior is so vast that 1,321 Earth-sized planets could fit inside it. Every mountain, every ocean, every city, every living thing on Earth could be replicated more than 1,000 times and still not fill Jupiter's volume. Jupiter contains more mass than all the other planets combined. If you could somehow gather every planet, moon, asteroid, and comet in the solar system except Jupiter and place them on a cosmic scale, Jupiter would still outweigh them all. It is a world of staggering proportions. Standing on a solid surface on Jupiter is impossible. There is no surface to stand on. Jupiter is a gas giant. Its outer layers are composed mostly of hydrogen and helium, swirling in powerful storms. Deeper down, the pressure becomes so intense that hydrogen transitions into a liquid metallic state. At the very center, there may be a solid core of rock and ice, but even that is uncertain. Jupiter is a world without a clear boundary between atmosphere and interior. Jupiter's most famous feature is the Great Red Spot, a storm larger than Earth that has been raging for at least 400 years. Wind speeds at the edges of the storm reach about 400 miles per hour. The storm is slowly shrinking. 100 years ago, it was about 3 times wider than Earth. Now it is only about 1 1/3 times wider. If the shrinking continues, the Great Red Spot may disappear within our lifetimes, but even as one storm fades, others emerge. Jupiter's atmosphere is constantly churning. Bands of clouds stretch around the planet, colored in shades of brown, white, and red. Lightning flashes in the depths. Winds howl at speeds far exceeding anything on Earth. Jupiter is a world of perpetual motion, a vast engine of atmospheric energy. Jupiter has at least 95 known moons, and more are being discovered regularly as our telescopes improve. The four largest moons, called the Galilean moons after Galileo, who first observed them in 1610, are worlds in their own right. Io is the most volcanically active body in the solar system. Its surface is constantly being resurfaced by volcanic eruptions. Tidal forces from Jupiter's gravity heat Io's interior, driving the volcanism. Io's surface is a patchwork of yellows, oranges, and reds, colored by sulfur compounds spewed from its volcanoes. Europa has a smooth, icy surface crisscrossed with cracks. Beneath the ice lies a global ocean that may contain twice as much water as all of Earth's oceans combined. Europa is one of the most promising places in the solar system to search for life. Where there is liquid water, there may be the possibility of life, even if that life is simple microbial organisms. Ganymede is the largest moon in the solar system, even bigger than the planet Mercury. It has its own magnetic field, a feature rare among moons. Ganymede's surface shows both ancient, heavily cratered terrain and younger, smoother regions shaped by tectonic activity. Callisto is heavily cratered, with one of the oldest surfaces in the solar system. Its surface has changed little over billions of years, preserving a record of the solar system's violent early history. Jupiter's gravity is so powerful that it acts like a cosmic vacuum cleaner, attracting and capturing many objects that might otherwise threaten the inner planets. Some scientists think Jupiter's presence has been crucial for Earth's development, reducing the number of large impacts Earth experienced over its history. Jupiter may have made it possible for complex life to evolve here by shielding us from some of the bombardment that would otherwise have struck our world. As we leave Jupiter behind and drift farther from the Sun, we come to the next giant, Saturn. Saturn is nearly as large as Jupiter, with a diameter of about 72,367 miles, about 9 times wider than Earth. 764 Earth-sized worlds could fit inside Saturn's volume, but Saturn is perhaps most famous not for its size, but for its magnificent ring system. The rings stretch from about 4,300 miles above Saturn's cloud tops to about 75,000 miles out. They are made of countless particles of ice and rock, ranging in size from tiny grains to house-sized boulders. The rings are remarkably thin, in most places only about 30 feet thick. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a piece of paper. No one knows exactly how old Saturn's rings are. They might have formed when Saturn did, about 4.6 billion years ago. Or they might be much younger, perhaps only a few 100 million years old, formed when a moon was torn apart by Saturn's gravity. Scientists are still debating this question. Saturn has at least 146 known moons. The largest, Titan, is bigger than Mercury. Titan is the only moon in the solar system with a thick atmosphere. In fact, Titan's atmosphere is thicker than Earth's. The surface pressure is about 1.5 times Earth's sea level pressure. Titan's atmosphere is mostly nitrogen, like Earth's, but it also contains methane. Titan has liquid on its surface, but not water. It is too cold for that. Instead, Titan has lakes and seas of liquid methane and ethane. These hydrocarbons rain from the sky, carve river channels, and collect in low-lying areas. Titan is the only place in the solar system besides Earth where we have confirmed stable bodies of surface liquid. Another fascinating moon is Enceladus. This small moon, only about 313 miles across, has geysers at its south pole that shoot water ice hundreds of miles into space. The water comes from a subsurface ocean. The Cassini spacecraft flew through these geysers and detected organic molecules, the building blocks of life. Enceladus is now considered one of the best places in the solar system to search for life. Saturn rotates quickly. One day on Saturn lasts only about 10.5 hours. This rapid rotation causes Saturn to bulge at the equator. The planet is noticeably flattened at the poles. Saturn's fast rotation and low density give it a unique shape among the planets. Standing on one of Saturn's moons and looking up, you would see a breathtaking sight. The ringed planet hanging in the sky, the rings stretching across the heavens, glowing softly in reflected sunlight. It would be a view unlike anything on Earth. A reminder that each world in the solar system offers its own unique perspective on the cosmos. As we leave Saturn behind, we begin to understand something profound. The gas giants dwarf Earth completely. Jupiter could swallow more than 1,000 Earths. Saturn could hold more than 700, and these are planets, not stars. The Sun is far larger still. Earth, which seemed so vast when we stood on its surface, has become incredibly small. In the context of the outer solar system, Earth is a tiny rocky world, lost among giants. And we have not yet ventured beyond the solar system. We have not yet seen the stars, the galaxies, the vast structures that make up the universe. Let us continue our journey. Let us drift farther still, into the cold outer reaches of the solar system. Beyond Saturn lie the ice giants, Uranus and Neptune. These worlds dwell in the cold darkness of the outer solar system, so far from the Sun that they receive only a fraction of the warmth that Earth enjoys. Uranus is the 7th planet from the Sun, orbiting at an average distance of about 1.8 billion miles. That is about 19 times Earth's distance from the Sun. Light from the Sun takes about 2 hours and 40 minutes to reach Uranus. By the time sunlight arrives, it is faint and weak, providing little warmth to this distant world. Uranus has a diameter of about 31,518 miles, about 4 times wider than Earth. The volume of Uranus equals roughly 63 planets the size of ours. If Earth were a marble, Uranus would be about the size of a softball. Uranus is unusual because it is tilted on its side. Its axis of rotation is tilted about 98 degrees from vertical. This means its poles sometimes point almost directly at the Sun. One pole experiences continuous sunlight for 42 years during Uranus's summer. During winter, it experiences continuous darkness for 42 years. The planet's equator, meanwhile, has more normal day-night cycles. No one knows for certain why Uranus is tilted so dramatically. The most likely explanation is that early in the solar system's history, the planet was struck by a large object that knocked it over. Uranus has at least 27 known moons. Most are named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. These moons are icy worlds, cold and distant, shaped by ancient geological processes we are only beginning to understand. Uranus also has a faint ring system, though it is far less prominent than Saturn's rings. The rings were discovered in 1977 and are composed of dark particles, making them difficult to see. As we drift even farther from the Sun, we come to Neptune. Neptune is the 8th and farthest planet from the Sun, orbiting at an average distance of about 2.8 billion miles, about 30 times Earth's distance from our star. Light from the Sun takes over 4 hours to reach Neptune. The planet was discovered in 1846, which means it has completed less than 2 full orbits since we first spotted it. 1 year on Neptune lasts about 165 Earth years. Neptune has a diameter of about 30,599 miles, about 4 times wider than Earth. Neptune's interior could accommodate 57 Earth-sized bodies. Like Uranus, Neptune is an ice giant, composed mostly of water, methane, and ammonia ices surrounding a rocky core. Wind speeds on Neptune are the fastest in the solar system, reaching up to 1,200 miles per hour. These extreme winds create large storms similar to Jupiter's Great Red Spot. The Voyager 2 spacecraft observed a storm called the Great Dark Spot in 1989. But when the Hubble Space Telescope looked at Neptune in 1994, the Great Dark Spot had disappeared and new storms had formed in its place. The weather on Neptune changes quickly and unpredictably. Neptune has at least 16 known moons. The largest is Triton, which is unusual because it orbits backward compared to the planet's rotation. This retrograde motion suggests Triton was not formed alongside Neptune, but was captured from the Kuiper belt. Triton is slowly spiraling inward. In about 3.5 billion years, it will either crash into Neptune or break apart from tidal forces, forming a ring system around the planet. Triton is one of the coldest objects in the solar system, with surface temperatures around -391 degrees Fahrenheit. Despite the extreme cold, Triton has geysers that erupt nitrogen gas and ice particles into space. These geysers suggest that Triton has some internal heat source, perhaps from tidal heating caused by Neptune's gravity. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies left over from the solar system's formation. This belt stretches from about 2.8 billion miles from the Sun to about 4.6 billion miles out. It is a vast reservoir of frozen objects, most of them small, composed of rock and ice. Pluto is the most famous Kuiper Belt object. It was considered the 9th planet from its discovery in 1930 until 2006, when astronomers redefined what constitutes a planet. Pluto did not make the cut because it has not cleared its orbit of other debris. It shares its orbital space with thousands of other objects. Pluto is small, only about 1,473 miles across, but it is fascinating. It has 5 known moons. The largest, Charon, is about half Pluto's size. Pluto and Charon are so close in size that they are sometimes called a binary system. They orbit a point in space between them, rather than Charon simply orbiting Pluto. NASA's New Horizons spacecraft flew past Pluto in July 2015, giving us our first close-up views. The images revealed a complex world with mountains made of water ice, vast plains of frozen nitrogen, and a thin atmosphere that extends much farther than expected. Pluto has a large heart-shaped region called Tombaugh Regio, named after Clyde Tombaugh, who discovered Pluto in 1930. There are other large Kuiper Belt objects. Eris, Makemake, and Haumea are all classified as dwarf planets. These objects show us that the outer solar system is more populated than we once thought. There might be thousands of dwarf planets in the Kuiper Belt, though most are too small and faint to detect with current telescopes. Beyond the Kuiper Belt is the Oort cloud, though no object in the Oort cloud has ever been directly observed. We know it exists because of comets. Long-period comets, those that take hundreds or thousands of years to orbit the Sun, come from the Oort cloud. The Oort cloud is enormous. It extends from about 2,000 astronomical units from the Sun to perhaps 100,000 astronomical units. That is nearly 2 light-years. The Oort cloud is so far away that the Sun's gravity barely holds on to it. A strong gravitational disturbance from a passing star could pull objects free. When a passing star's gravity disturbs an Oort cloud object, it can fall toward the inner solar system, becoming a comet. As the comet approaches the Sun, its icy surface begins to vaporize, creating the glowing tail that makes comets so striking in our night sky. The Oort cloud marks the true edge of the solar system. Beyond it, the Sun's influence becomes negligible. Space becomes interstellar, the realm between stars, and in all this vast volume from the Sun to the Oort cloud, Earth is one small rocky planet. 8,000 miles across, orbiting 1 astronomical unit from the Sun, the solar system extends for trillions of miles, and Earth occupies only a tiny fraction of that space. In a proportional model, where the Sun equals the size of a basketball, Earth would be no larger than a peppercorn positioned 26 feet away. Neptune would be over 800 feet distant. The Oort cloud would extend for miles in every direction. The solar system is vast, and Earth, in all that vastness, is almost invisible. Let us leave the solar system now. Let us venture into the space between stars. Now let us leave the solar system entirely. Let us venture out to the nearest stars. This is where distances become so large that our usual measurements stop making sense. Miles and kilometers lose meaning. We must use light years instead. A light year is the distance light travels in 1 year. Light moves at 186,000 miles per second. In 1 year, light travels about 5.88 trillion miles. That is the scale we must now think in, not millions of miles, not billions, but trillions. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system. It lies about 4.24 light-years away. That is roughly 25 trillion miles from Earth. To put this in perspective, if the distance from Earth to the Sun was represented by 1 inch, the distance to Proxima Centauri would be about 4 miles. Remember how the Sun is 93 million miles from Earth. Proxima Centauri is about 268,000 times farther away than the Sun. The gap between stars is incomprehensibly vast compared to the distances within our solar system. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object. It has been traveling for over 47 years and is now about 15 billion miles from Earth, moving at about 38,000 miles per hour. At that speed, Voyager would still need 73,000 years to reach Proxima Centauri, and it is not even aimed in that direction. Even with hypothetical future technology, if we could build a spacecraft that traveled at 10% the speed of light, far beyond anything we can currently achieve, it would still take over 42 years to reach Proxima Centauri. The distances between stars are genuinely, almost incomprehensibly vast, and Proxima Centauri is our closest neighbor. Proxima Centauri itself is a red dwarf, the most common type of star in the galaxy. It is much smaller and cooler than the Sun. Its diameter is only about 129,000 miles, roughly 14% of the Sun's diameter. It has only about 12% of the Sun's mass. Because Proxima Centauri is so small and cool, it burns its fuel very slowly. It will keep shining for trillions of years, long after the Sun has died. In fact, no red dwarf anywhere in the universe has ever died of old age. The universe itself is not old enough yet for any red dwarf to have exhausted its fuel. Proxima Centauri is also a flare star. It regularly produces powerful flares, sudden releases of energy that can temporarily increase its brightness. These flares would be dangerous for any planets hoping to host life. The radiation from a flare could strip away a planet's atmosphere or sterilize its surface. Interestingly, Proxima Centauri does have at least 2 known planets. Proxima Centauri b orbits in the star's habitable zone, the region where liquid water could exist on a planet's surface. But given the flares and radiation, life there seems unlikely. Still, it is fascinating that the nearest star to us has planets of its own. Proxima Centauri is part of a triple star system with Alpha Centauri A and Alpha Centauri B. All 3 stars are gravitationally bound, forming a single system. Alpha Centauri A and B are Sun-like stars, brighter and larger than Proxima. They orbit each other while Proxima orbits the pair at a great distance. From Proxima Centauri, if you looked back toward our solar system, the Sun would appear as a bright star. But Earth would be completely invisible, lost in the glare of the Sun, a tiny dot too close and too faint to detect. Even with a powerful telescope, separating Earth from the Sun's light would be nearly impossible. At this distance, Earth has vanished. It is no longer visible. It is no longer detectable. It has become, for all practical purposes, non-existent in the vastness of space. Beyond Alpha Centauri, the next nearest star is Barnard's star, about 6 light-years away. It is another red dwarf, small and dim, discovered in 1916 by astronomer Edward Emerson Barnard. Barnard's star is notable for its high proper motion. It moves across the sky faster than any other star, a result of its relative proximity and its motion through space. Sirius, the brightest star in Earth's night sky, lies about 8.6 light-years away. Sirius is actually a binary star system, consisting of Sirius A, a bright blue-white star about twice the mass of the Sun, and Sirius B, a white dwarf. Sirius B is the remnant of a star that exhausted its fuel and collapsed into a dense, Earth-sized object. A teaspoon of material from Sirius B would weigh about 5 tons on Earth. Sirius appears so bright in our sky not because it is exceptionally luminous, but because it is relatively close. Many stars are far more luminous than Sirius, but they are so distant that they appear faint from Earth. As we venture farther, we encounter Betelgeuse, one of the most famous stars visible from Earth. Betelgeuse is a red supergiant located in the constellation Orion, about 700 light-years away. It is so large that if you placed it where the Sun is, it would extend past the orbit of Mars. Betelgeuse's diameter is roughly 700 times larger than the Sun's. Betelgeuse is nearing the end of its life. It has exhausted much of its hydrogen fuel and is now fusing heavier elements in its core. Eventually, Betelgeuse will explode as a supernova, an event so bright it will be visible from Earth during the daytime. When that happens, Betelgeuse will briefly outshine the entire galaxy. But predicting exactly when this will occur is difficult. It could happen tomorrow, or it could be 100,000 years from now. The light we see when we look at Betelgeuse left that star around the time the Crusades were ending on Earth. We are seeing Betelgeuse not as it is now, but as it was 700 years ago. If Betelgeuse exploded today, we would not know for another 700 years. The light from that explosion would still be traveling toward us across the immense gulf of space. All the stars we can see with our naked eyes belong to our galaxy, the Milky Way. Every single point of light in the night sky, every constellation, every star you have ever noticed, is part of our galactic home, and most of them are within a few thousand light-years of Earth. The Milky Way contains somewhere between 100 billion and 400 billion stars. Our Sun is just one of them. An ordinary yellow dwarf in an ordinary location, about 26,000 light-years from the galactic center. At the scale of the stars, Earth is no longer just small. It has completely disappeared. Even the Sun is now just one star among hundreds of billions, and Earth is far too tiny to register at all. If you were standing on a planet orbiting Proxima Centauri and looked back toward our solar system, you would see the Sun, a bright star, perhaps slightly brighter than some others. But you would not see Earth, you would not see Jupiter, you would not see Saturn's rings. All the planets, all the moons, all the asteroids and comets would be invisible. Lost in the glare of the Sun, the solar system, which seemed so vast when we explored it, has become a single point of light, and Earth within that point has vanished. This is a profound shift in perspective. We are no longer talking about Earth being small compared to the Sun or Jupiter. We are talking about Earth being invisible, undetectable. A world that exists but cannot be seen from even our nearest stellar neighbors, and we have only just begun to explore the true scale of the cosmos. The stars are just the beginning. Beyond them lie the structures of the galaxy itself, the spiral arms, the galactic core, the vast distances between one side of the Milky Way and the other. Let us continue our journey. Let us zoom out further still and see our galaxy as a whole. All the stars we have discussed so far, from Proxima Centauri to Betelgeuse, are part of our galaxy, the Milky Way. A vast spiral structure containing hundreds of billions of stars, stretching across 100,000 light-years of space. To understand the scale of the Milky Way, we must shift our perspective once again. We are no longer looking at individual stars. We are looking at the structure that contains them all, a galaxy. An island of stars floating in the vast darkness of space, the Milky Way is a barred spiral galaxy. This means it has a central bar-shaped structure made of stars, with spiral arms extending from the ends of the bar. Our Sun is located in one of these spiral arms, a minor arm called the Orion Spur, about 26,000 light-years from the galactic center. We are not in the middle of anything special. We are in the suburbs of the galaxy, in a relatively quiet region where stars are not too densely packed. This is probably a good thing for life on Earth. The spiral arms are violent places, filled with young, massive stars that live fast and die in spectacular supernova explosions. The intense radiation from these stars and their deaths would make life difficult, perhaps impossible. Being between the spiral arms gives Earth a safer environment, quieter, more stable. Less bombarded by high-energy radiation, it is one of many factors that may have allowed complex life to evolve here. The Milky Way's structure is complex and beautiful. At the center lies the galactic bulge, a dense concentration of old stars. This region is about 10,000 light-years across. The stars here are packed much more densely than in our neighborhood. If you lived on a planet near the galactic center, your night sky would be filled with thousands of bright stars, making the night almost as bright as twilight on Earth. At the very center of the galactic bulge sits Sagittarius A star, a supermassive black hole. This black hole has a mass of about 4 million times the mass of the Sun. It is relatively quiet now, not actively consuming large amounts of material, but it occasionally flares up when gas or even a star falls into it. Stars orbit this black hole at incredible speeds. One star, called S2, orbits the black hole once every 16 years at speeds reaching 5% the speed of light. At its closest approach, S2 comes within about 11 billion miles of the black hole, about the distance from the Sun to Saturn. Observing these stars has allowed scientists to test Einstein's theory of general relativity in extreme gravitational conditions. Around the galactic center are the spiral arms. These are regions where gas and dust are compressed, triggering waves of star formation. The spiral arms appear bright because they contain lots of young, hot, blue stars. These massive stars burn their fuel quickly, rarely lasting more than a few million years. By the time they die, they have barely moved from where they were born, so they stay in the spiral arms, lighting them up. Our Sun, being an older, more stable star, has had time to drift away from the spiral arm where it formed. We are now between spiral arms, in a quieter region. The Sun takes about 225 million years to complete one orbit around the galactic center. This is called a galactic year or cosmic year. Think about that for a moment. In the time it takes for our Sun to go around the galaxy once, entire species rise and fall on Earth. The last time the Sun was at this point in its orbit, dinosaurs were just beginning to emerge. The time before that, the supercontinent Pangaea was still intact. Earth has been around for about 20 galactic years. The universe has existed for about 60 galactic years. These timescales are almost incomprehensible. They stretch far beyond human lifetimes, beyond the span of civilizations, beyond the age of our species. The Milky Way has several distinct regions. The galactic disk, where most of the stars reside, is relatively thin, only about 1,000 light-years thick in most places, but 100,000 light-years across. Surrounding this disk is the galactic halo, a roughly spherical region containing old stars and globular clusters. Globular clusters are dense spherical collections of hundreds of thousands or even millions of stars. M13, also known as the Great Globular Cluster in Hercules, contains about 300,000 stars packed into a region about 145 light-years across. At the center of M13, stars are so densely packed that if you lived on a planet there, your night sky would be filled with thousands of stars as bright as Venus appears in our sky. The night would never truly be dark. The galactic halo extends about 130,000 light-years from the galactic center. The stars in the halo are among the oldest in the galaxy, formed when the Milky Way was just beginning to take shape. These stars are metal-poor, meaning they contain very few elements heavier than hydrogen and helium. They formed before many generations of stars had lived and died, before supernovae had enriched the galaxy with heavier elements. The halo also contains dark matter. We cannot see dark matter directly, but we can detect its gravitational effects. The Milky Way's dark matter halo extends even farther than the visible halo, possibly out to 600,000 light-years or more. Most of the Milky Way's mass is actually dark matter, not stars and gas. The Milky Way is not isolated. It has numerous satellite galaxies orbiting it. The two most famous are the Large and Small Magellanic Clouds. Both are visible from the southern hemisphere as fuzzy patches in the night sky. The Large Magellanic Cloud contains about 10 billion stars and is roughly 14,000 light-years across. The Small Magellanic Cloud is even smaller. Both Magellanic Clouds are being slowly torn apart by the Milky Way's gravity. They are leaving streams of gas and stars in their wake as they orbit. Eventually, they will be completely absorbed into the Milky Way. This process of galactic cannibalism is how large galaxies like ours grow over time. There are dozens of other smaller satellite galaxies orbiting the Milky Way. Most are dwarf galaxies containing only a few million stars. These satellites are important for understanding how galaxies form and evolve. Large galaxies like the Milky Way grow through mergers, absorbing smaller galaxies over billions of years. The satellites we see today are the leftovers that have not merged yet. The Milky Way is also moving through space. It is not stationary. Along with the entire local group of galaxies, it is being pulled toward a massive structure called the Great Attractor, located about 200 million light-years away. But more immediately, the Milky Way is on a collision course with the Andromeda Galaxy. In about 4.5 billion years, the two galaxies will merge into a single large elliptical galaxy. The merger will be a slow, graceful dance lasting millions of years. Despite containing hundreds of billions of stars each, the galaxies are so mostly empty space that actual collisions between stars will be incredibly rare. As the galaxies approach, their shapes will distort. Tidal forces will pull streams of stars out into space. The spiral arms will be disrupted. Eventually, the two galaxies will pass through each other, their gravity pulling them back together. They will merge and remerge several times before finally settling into a single structure. By then, the night sky from Earth, if Earth still exists, will look completely different. The Milky Way is home to a staggering diversity of objects. Not just stars, but nebulae, star clusters, black holes, neutron stars, white dwarfs, planets, and perhaps even other civilizations. Star-forming regions like the Orion Nebula show us where new stars are being born. The nebula is a cloud of gas and dust about 24 light-years across, located about 1,344 light-years away. Inside it, hundreds of stars are forming from collapsing clouds of hydrogen. The intense radiation from newly formed stars lights up the surrounding gas, creating the glowing clouds we see through telescopes. About 4.6 billion years ago, our Sun formed in a similar nebula. The Sun and probably hundreds of other stars condensed from the same cloud of gas. Those sibling stars have long since drifted apart, scattered across the galaxy by the motions of stars and the rotation of the Milky Way. We may never know which stars are the Sun's siblings. The Milky Way also contains stellar remnants, white dwarfs, the cooling remnants of Sun-like stars. Neutron stars, the collapsed cores of massive stars, so dense that a teaspoon of neutron star material would weigh about 4 billion tons. Black holes, regions where gravity is so strong that nothing, not even light, can escape. And then there are the planets. Since the first exoplanet was confirmed in the early 1990s, we have discovered thousands of planets orbiting other stars in the Milky Way. Some are gas giants larger than Jupiter. Some are rocky worlds similar in size to Earth. Some orbit in their star's habitable zone, where liquid water could exist on the surface. Current estimates suggest there may be billions of Earth-sized planets in the Milky Way alone, billions of worlds where the conditions might be right for life. We do not know if life exists on any of them. We have only one confirmed example of life, Earth. But the sheer number of potentially habitable worlds suggests that life might not be as rare as we once thought. At this scale, the transformation is complete. Earth has not merely shrunk. It has effectively disappeared. The planet that once felt immeasurable from the surface is now beyond detection. We are talking about a galaxy 100,000 light-years across, containing hundreds of billions of stars. And somewhere in that vast structure, about 2/3 of the way out from the center, in a minor spiral arm, orbits an ordinary yellow star. And around that star, at a distance of 93 million miles, is a small rocky planet, Earth. If you compress the Milky Way into a structure 100 feet across, our entire solar system would measure thinner than a human hair's width, and Earth would be far, far smaller than that. At this scale, Earth would not just be invisible, it would be smaller than an atom in the model. We have not yet left our own galaxy. This is only the beginning of the true scale of the universe. Beyond the Milky Way lie other galaxies, billions of them, scattered across billions of light-years of space, and Earth, in all that vastness, is a speck so small that it defies comprehension. But even knowing this, even understanding how small Earth is, we must remember something important. Size is not the same as significance. Earth may be tiny, but it is home. It is the only place we know where life exists, the only place where consciousness has arisen to contemplate the cosmos. In all the vastness of the Milky Way, we know of only one world that harbors life, and that world is here, on this tiny planet, orbiting this ordinary star, in this quiet corner of the galaxy. Let us continue outward, beyond the Milky Way, into the realm of galaxies, where the scale becomes so vast that even our galaxy, immense as it is, becomes just one small point of light among countless others. The Milky Way is not alone in space, it has neighbors. Other galaxies drifting through the cosmic void, bound together by gravity into what astronomers call the local group. The local group is our immediate galactic neighborhood. It contains about 50 galaxies, most of them small dwarf galaxies containing only a few million or billion stars, but 3 galaxies dominate this collection: the Milky Way, Andromeda, and Triangulum. The largest member of the local group is Andromeda, also called M31 or the Andromeda Galaxy. Andromeda is a spiral galaxy much like our own, but larger. It contains about 1 trillion stars, more than twice what the Milky Way has. Its diameter is about 220,000 light-years, more than twice the Milky Way's width. Andromeda is located about 2.5 million light-years from us. That means the light we see from Andromeda today left that galaxy 2.5 million years ago. When that light began its journey, early human ancestors were just beginning to walk upright on the plains of Africa. The light has been traveling through empty space ever since, crossing the vast gulf between galaxies until it finally reaches our eyes tonight. Andromeda is approaching us. It is moving toward the Milky Way at about 70 miles per second. In about 4.5 billion years, the two galaxies will collide, but collision is perhaps the wrong word. Galaxies do not crash into each other like solid objects. They merge, they pass through each other, their stars so far apart that actual collisions between individual stars are vanishingly rare. When the merger happens, the night sky will change dramatically. Andromeda will grow larger and larger over millions of years until it dominates the sky. The spiral structures of both galaxies will be distorted by tidal forces. Streamers of stars will be pulled out into space. The two galaxies will pass through each other, then fall back together, merging and re-merging until they finally settle into a single elliptical galaxy. The next largest member of the local group is Triangulum, also called M33. It is a spiral galaxy containing about 40 billion stars and spanning roughly 60,000 light-years. Triangulum is located about 3 million light-years from the Milky Way. It is one of the most distant objects visible to the naked eye from Earth, though you need very dark skies and sharp eyes to spot it. The rest of the local group consists mostly of dwarf galaxies. Small collections of stars, often irregularly shaped, orbiting the larger galaxies. The large and small Magellanic Clouds, visible from the southern hemisphere, are part of this group. So are dozens of smaller dwarf galaxies with names like Sculptor, Fornax, Leo I, and Draco. These dwarf galaxies are the leftovers of galaxy formation. They are the small building blocks that were never absorbed into larger structures. Over time, many of them will be consumed by the Milky Way or Andromeda. Galactic cannibalism is an ongoing process. Large galaxies grow by eating smaller ones. The local group spans about 10 million light-years. If the Milky Way were the size of a coin, the local group would be about the size of a large room. That seems vast, but it is just the beginning. The local group is part of a much larger structure called the Virgo supercluster. A supercluster is a collection of galaxy groups and clusters, all loosely bound together by gravity. The Virgo supercluster spans about 110 million light-years and contains at least 100 galaxy clusters and groups. The total number of galaxies is difficult to estimate, but it likely numbers in the tens of thousands. The total number of stars is almost beyond comprehension. Somewhere around 100 trillion stars. The dominant structure in the Virgo supercluster is the Virgo cluster itself. Located about 54 million light-years from us, the Virgo cluster contains between 1,200 and 2,000 galaxies. Some of these galaxies are enormous, far larger than the Milky Way. At the heart of the Virgo cluster sits M87, a giant elliptical galaxy. M87 contains about 1 trillion stars. It is famous for being the first galaxy where we directly imaged a black hole. In 2019, the Event Horizon Telescope collaboration released an image showing the shadow of M87's supermassive black hole. The black hole has a mass about 6.5 billion times the mass of the Sun. The image of M87's black hole was a landmark achievement. For the first time, humanity could see the shadow cast by a black hole's event horizon. The dark circle in the center of the image is not the black hole itself, but the region from which no light can escape. Around it glows a ring of superheated matter spiraling toward oblivion. If we made a scale model where the Milky Way was the size of a coin, the Virgo supercluster would be about the size of a large city. Everything we have discussed up to this point, the Sun, the solar system, the distances between stars, the Milky Way itself, all of that would fit on a coin in this model. And Earth would be far smaller than any particle you could see with a microscope. At this scale, the transformation is profound. Earth has not merely shrunk, it has become essentially invisible. The planet that once seemed so vast from its surface is now a speck so small that it cannot be represented in any meaningful way. And yet, even knowing this, we must remember something important. Size is not the same as significance. Earth may be tiny, but it is home. It is the only place we know where life exists, the only place where consciousness has arisen to contemplate the cosmos. In all the vastness of the Virgo supercluster, with its tens of thousands of galaxies and trillions of stars, we know of only one world that harbors life, and that world is here. On this tiny planet, orbiting this ordinary star, in this quiet corner of the local group, the Virgo supercluster is not the final structure. It is itself part of something even larger. Something that redefines our understanding of cosmic scale once again, but that is a story for the next part of our journey. For now, let us pause here. Let us feel the weight of these distances. Let us appreciate the immensity of the structures we have described, the local group, the Virgo supercluster, tens of thousands of galaxies, trillions of stars. And somewhere in all that vastness, a small rocky planet orbiting a yellow star. Earth is small, but it is ours, and that makes all the difference. Let us continue outward. Beyond the Virgo supercluster, into the largest structures we know, we have seen how galaxies cluster into groups and clusters, but the story does not end there. These structures are themselves part of an even larger pattern, a pattern that stretches across the entire observable universe, a pattern that redefines, once again, our understanding of cosmic scale. In 2014, a team of astronomers led by R. Brent Tully at the University of Hawaii redefined our understanding of our cosmic neighborhood. They mapped the motions of thousands of galaxies, not just their positions. They looked at how galaxies move relative to each other, pulled by the gravity of nearby matter. They traced the flow of galaxies through space like rivers flowing toward the sea. What they found was a massive structure they named Laniakea. The name comes from Hawaiian words meaning immense heaven. It is a fitting description. Laniakea is a supercluster of superclusters. It contains about 100,000 galaxies spread across 520 million light-years. The total mass is about 100 million billion times the mass of the Sun. Everything within this region is gravitationally bound, flowing toward a central point like water draining toward a sink. That central point is called the Great Attractor. Located about 150 million light-years away, the Great Attractor is a gravitational focal point. It is a region of intense mass pulling galaxies toward it. The Milky Way, along with everything else in Laniakea, is moving toward the Great Attractor at about 370 miles per second. We have been falling toward it for billions of years. The nature of the Great Attractor was a mystery for many years. It lies hidden behind what astronomers call the zone of avoidance, the region of space obscured by the dust and gas of the Milky Way's disk. Our own galaxy blocks our view. But using X-ray and radio observations, astronomers have peered through the veil. They found that the Great Attractor is not a single object, but a concentration of galaxy clusters. The Norma cluster is the dominant component, a massive collection of galaxies near the center. Together, these clusters create a gravitational well deep enough to pull in everything within hundreds of millions of light-years. But there is a deeper mystery. The Great Attractor itself seems to be moving toward something even larger. Some observations suggest that galaxy clusters across a huge region of the universe are moving in a coherent direction, being pulled toward something beyond the observable universe. This phenomenon is called dark flow. It is one of the most intriguing puzzles in modern cosmology. What lies beyond our cosmic horizon? What force could pull entire superclusters of galaxies? We do not yet know, perhaps we never will. Laniakea is just one thread in a much larger tapestry. When we step back and look at the universe on the largest scales, we see a pattern emerge. A structure so vast and so intricate that it defines the architecture of the cosmos itself. We call it the cosmic web. Imagine a three-dimensional spider web stretching across billions of light-years. Long filaments of galaxies crisscross through space. Where these filaments intersect, they form massive clusters, dense knots in the web. Between the filaments are vast, empty regions called voids. These voids are the largest structures in the universe, yet they are defined by what they lack: matter. The filaments are made of galaxies, gas, and dark matter. They stretch for hundreds of millions of light-years. The clusters at their intersections are the densest regions in the universe, containing thousands of galaxies packed into relatively small volumes. When we look at these clusters through telescopes, we see not just galaxies, but the glowing X-ray halos of hot gas filling the space between them. This gas is heated to millions of degrees by the gravitational energy of the cluster. The voids, by contrast, are almost completely empty. They contain very few galaxies, mostly just hydrogen gas and dark matter drifting through darkness. These voids can be hundreds of millions or even billions of light-years across. They are so empty that if you were somehow placed in the center of one, you might see only a handful of faint galaxies scattered across the entire sky. The universe would seem almost devoid of structure. The KBC void, named after the astronomers Keenan, Barger, and Cowie who discovered it, is one of the largest known voids. It is about 2 billion light-years across. Our Milky Way sits near the edge of this void. This means that our cosmic neighborhood is emptier than average. We are living in a region of low density, surrounded by shells of higher density farther out. This may have implications for how we measure the expansion of the universe. Our location in a void might affect our observations in subtle ways. The existence of the cosmic web is a direct result of the early universe's conditions. Shortly after the Big Bang, tiny fluctuations in the density of matter existed. These fluctuations were incredibly small, only about 1 part in 100,000, but they were enough. Slightly denser regions had slightly stronger gravity. Over billions of years, these regions attracted more matter. Slightly less dense regions lost matter to their surroundings. Gravity amplified these differences, pulling matter into filaments and draining the voids. Dark matter plays a crucial role in this process. Dark matter makes up about 85% of the matter in the universe. We cannot see it. We detect it only through its gravitational effects. Dark matter formed the scaffolding for the cosmic web. Its gravity pulled normal matter, the atoms and molecules that make up stars and planets in us, into the filaments and clusters we see today. Without dark matter, the universe would look very different. Galaxies might not have formed at all. Computer simulations of the universe's evolution, like the Millennium Simulation and the Illustris project, show how this structure arises. Scientists input the conditions of the early universe into powerful computers and let the simulation run forward in time, following the laws of gravity and physics. What emerges is a cosmic web remarkably similar to what we observe: filaments, clusters, voids. The match between simulation and observation is striking. It is strong evidence that our understanding of cosmic structure formation is fundamentally correct, but mysteries remain. The distribution of voids and filaments may hold clues to the nature of dark energy, the mysterious force causing the universe's expansion to accelerate. Some researchers think that studying the shapes and sizes of voids could reveal how dark energy behaves on the largest scales. Others wonder whether the cosmic web structure could tell us something about the very first moments after the Big Bang, when the universe was filled with quantum fluctuations that would eventually grow into galaxies. The scale of the cosmic web is almost impossible to grasp. Filaments span billions of light years. Voids contain almost nothing, yet they define the shape of the cosmos. Galaxies like our own are tiny specks clinging to the threads of this web. The Milky Way, which seemed so vast just moments ago in our journey, is now just one galaxy among 100,000 in Laniakea. And Laniakea itself is just one structure among many in the cosmic web. At this scale, Earth has become something beyond small. It has become inconceivable. If Laniakea were the size of a large city, the Milky Way would be the size of a coin, and Earth would be far smaller than a single atom within that coin. The ratio between Earth and the cosmic web is so vast that language fails, numbers fail, our minds struggle to hold the comparison. And yet, for all its smallness, Earth remains precious. Because in all this vastness, as far as we know, it is the only place where life exists, the only place where consciousness has arisen to look out at the cosmic web and understand it. We are the universe aware of itself. We are matter organized in such a way that it can contemplate its own existence. Let us continue our journey, one more step outward. To the very edge of everything we can observe, we have traveled far on this journey, from Earth to the Moon, from the Sun to the planets, from our solar system to the stars. From the Milky Way to clusters of galaxies, from superclusters to the cosmic web itself. But now we approach a boundary, not a physical wall, but a limit imposed by the nature of the universe itself. We approach the edge of the observable universe. The observable universe is everything we can theoretically see. It is limited by two factors: the speed of light and the age of the universe. Light travels fast, but it is not instantaneous. It moves at 186,000 miles per second. Nothing can travel faster. This means that light from distant objects takes time to reach us, and if an object is far enough away, its light has not yet had time to arrive. The universe is about 13.8 billion years old. You might think this means we can see objects up to 13.8 billion light-years away. But the universe has been expanding the entire time. Space itself has been stretching. So an object that emitted light 13 billion years ago has moved much farther away during the time its light traveled toward us. When we account for this expansion, the observable universe turns out to be much larger than 13.8 billion light-years. The radius of the observable universe is about 46.5 billion light-years. That makes the diameter roughly 93 billion light-years. This is the farthest we can possibly see, even in principle. Beyond this boundary, light has not had time to reach us. There may be more universe out there, perhaps infinitely more, but we cannot observe it. It is beyond our cosmic horizon. Within this observable sphere, astronomers estimate there are about 2 trillion galaxies, 2 trillion, each one containing anywhere from millions to trillions of stars. The total number of stars in the observable universe is estimated at around 200 billion trillion. That is 2 followed by 23 zeros. If every star were represented by a grain of sand, you would need several Olympic-sized swimming pools to hold them all. And Earth, in all this vastness, is one planet, orbiting one star. In one galaxy, among 2 trillion galaxies, the numbers become so large that they lose meaning. Our minds cannot truly grasp what 2 trillion galaxies means. We can write the number. We can do mathematics with it, but we cannot visualize it. It is simply too vast. When we look deep into space with our most powerful telescopes, we are also looking back in time. The light from distant galaxies took billions of years to reach us. We are seeing those galaxies not as they are now, but as they were when the light left them. The farther we look, the farther back in time we see. The most distant galaxies ever observed appear as they were just a few 100 million years after the Big Bang. These are ancient galaxies. Primitive, small, they show us what the early universe looked like when the first stars were just beginning to form. Some of these galaxies are so far away that their light has been traveling toward us for over 13 billion years. By the time that light reaches our telescopes, those galaxies may have changed beyond recognition. They may have merged with other galaxies. They may have been torn apart. We have no way to know what they look like today. The most distant object we can detect is the cosmic microwave background radiation. This is the afterglow of the Big Bang itself. About 380,000 years after the Big Bang, the universe cooled enough for light to travel freely through space for the first time. Before that, the universe was so hot and dense that light could not escape. It was trapped in a glowing fog of particles, but when the universe cooled, light broke free. That light has been traveling through space ever since, stretched by the expansion of the universe into microwaves. It fills the entire sky. It is the oldest light in the universe. When we observe the cosmic microwave background, we are seeing the universe as it was 380,000 years after the Big Bang. We are looking back 13.8 billion years. We are seeing the edge of the observable universe. We cannot see farther than this. Before this moment, the universe was opaque. Light could not travel. There is a wall beyond which we cannot observe, not because of technological limitations, but because of the fundamental nature of the universe itself. The observable universe is not the entire universe. It is just the part we can see. The actual universe may be far larger. It may even be infinite. We do not know. Some theories suggest the universe is finite but unbounded, like the surface of a sphere. If you traveled in one direction long enough, you might eventually return to where you started. Other theories suggest the universe is truly infinite, extending forever in all directions. If that is true, then the observable universe is just a tiny bubble within an endless expanse. If the universe is infinite, then everything that can happen will happen, not just once but infinitely many times. There would be infinite copies of Earth, infinite copies of you. Infinite variations of every possible event. This is a strange and unsettling idea, but it is a logical consequence of an infinite universe with finite arrangements of matter. The observable universe is also expanding, not just growing larger as light from more distant regions reaches us, but expanding in the sense that space itself is stretching. Galaxies are moving away from each other, not because they are traveling through space, but because the space between them is increasing. The farther away a galaxy is, the faster it appears to be receding. This is Hubble's law, discovered by Edwin Hubble in the 1920s. The expansion of the universe is accelerating. Distant galaxies are moving away from us faster and faster. This acceleration is driven by something called dark energy, a mysterious force that makes up about 68% of the universe's total energy. We do not know what dark energy is. We can measure its effects, but we do not understand its nature. It is one of the greatest mysteries in modern physics. Because the expansion is accelerating, galaxies that are currently within our observable universe will eventually move beyond our cosmic horizon. In the far future, trillions of years from now, if any observers still exist, they will see a very different universe. Most galaxies will have receded beyond the observable limit. The night sky will be much emptier. future civilizations might conclude they live in a lonely universe, with only their local group of galaxies visible. They would have no way to know about the billions of other galaxies that once filled the sky. The observable universe contains structures on every scale: planets, stars, galaxies, clusters. Superclusters, filaments, voids, all of it held together by gravity and shaped by the expansion of space, all of it governed by the same physical laws. The same forces that hold atoms together also hold galaxies in clusters. The same gravity that keeps Earth in orbit around the Sun also pulls entire superclusters through space. And in all this vastness, Earth is a single point, a single world. Among countless billions of worlds that may exist, we have found thousands of planets orbiting other stars. Some are rocky like Earth, some orbit in their star's habitable zone, where liquid water could exist. The number of potentially habitable planets in the observable universe is staggering: billions. Perhaps hundreds of billions, and yet we know of only one world where life exists: Earth. It is possible we are alone. It is possible life is so rare, so improbable, that it has arisen only here. Or it is possible that life is common, scattered across countless worlds, but so far away and so alien that we will never detect it. We do not know. And that uncertainty is part of what makes our place in the universe so profound. We stand on a tiny world, looking out at a cosmos of unimaginable scale, wondering if anyone else is looking back. The observable universe is the stage on which all of existence plays out. It is vast, ancient, beautiful, and within it, Earth is almost invisible, but Earth is also precious, because it is home. And as far as we know, it is the only home life has ever known. Let us continue our journey. Let us look at Earth from one final perspective. A perspective that has humbled humanity and reminded us of our place in the cosmos. In 1990, a spacecraft called Voyager 1, which had completed its primary mission and was heading out of the solar system, turned its camera back toward Earth and took a photograph. The image was captured from a distance of about 3.7 billion miles, about 40 times farther from the Sun than Earth. At that distance, Earth appeared as a tiny pale blue dot, less than a single pixel in size, suspended in a beam of scattered sunlight. This photo, taken from the edge of our solar system, is one of the most profound images ever captured. It shows Earth as it truly is in the context of space, a tiny speck, barely visible. Floating in an enormous void, the astronomer Carl Sagan reflected on this image in his book Pale Blue Dot. He wrote about how every human who ever lived out their entire life on that tiny speck. Every king and peasant, every hero and villain, every creator and destroyer of civilization. All of them lived on that dot, all our triumphs and tragedies, all our wars and peace. Everything that has ever mattered to humanity happened on that barely visible point of light. Sagan's words capture something essential. When we see Earth from this distance, the borders we fight over disappear. The nations we divide ourselves into become meaningless. The resources we compete for, the status we seek, the conflicts that consume us, all of it plays out on a stage so small that from a modest distance, it vanishes entirely. This perspective does not make our lives meaningless. If anything, it makes them more precious, because as far as we know, that pale blue dot is the only place in the universe where life exists. And conscious, intelligent life may be even rarer. The pale blue dot is not just our home. It may be the only home life has ever known. The photo was taken from a distance that is nothing on cosmic scales. 3.7 billion miles sounds like a lot, but it is only about 40 times the distance from Earth to the Sun. It is barely out of the solar system. From the nearest star, Earth would be completely invisible, lost in the glare of the Sun. From another galaxy, our entire solar system would be invisible. And yet that tiny pale blue dot is home to everything we know, every thought, every emotion, every moment of joy and sorrow. All of it happened there. Every story ever told, every song ever sung. Every work of art ever created, every scientific discovery, every act of kindness, every cruelty, all of it on that dot. The pale blue dot image reminds us that Earth is fragile. That thin blue line of atmosphere clinging to the surface is all that protects us from the vacuum of space. It is a delicate shell, easily disrupted. We have already changed Earth's atmosphere through our activities. We have altered the climate. We have driven species to extinction. We have scarred the landscape with our cities and industries. And there is nowhere else to go. Not yet, perhaps not ever. We are bound to this planet. This is our only home. If we damage it beyond repair, there is no backup, no second Earth waiting for us. We must take care of this world because it is all we have. The pale blue dot also reminds us of our shared humanity. When you look at Earth from space, you do not see borders. You do not see nations or races or religions. You see one world, one planet, shared by all of us. The artificial divisions we create seem absurd when viewed from this perspective. We are all passengers on the same small world, traveling through space together. Astronauts who have seen Earth from space often describe a profound shift in perspective. They call it the overview effect. Seeing Earth as a whole, floating in the darkness, fragile and beautiful, changes something deep inside. It makes the conflicts between nations seem petty. It makes the idea of war seem insane. How can we fight over pieces of a world so small? The pale blue dot perspective also highlights the courage required to explore. Voyager 1, the spacecraft that took the photo, is now the most distant human-made object. It has traveled farther from home than anything we have ever built. It is moving at about 38,000 miles per hour, and it will keep moving for thousands of years, long after it stops sending signals back to Earth. Eventually, it will drift among the stars, a silent messenger from a small blue world. Voyager carries a golden record, a disc containing sounds and images from Earth, music. Greetings in many languages, pictures of humans and animals and landscapes. It is a message to the universe, a way of saying we were here, we existed, we created, we hoped. The record will outlast our civilization. Long after humanity is gone, long after Earth itself is gone, Voyager will still be drifting through space, carrying its message. It is both humbling and inspiring. Humbling because it reminds us how temporary we are. Inspiring because it shows what we can achieve when we reach beyond our world. The pale blue dot image also raises questions. If Earth is so small, and we are so small, does anything we do matter? If the universe is so vast, and we are so insignificant, why should we care about our lives, our struggles, our achievements? This is a question philosophers have grappled with for centuries. And there is no single answer, but here is one way to think about it. The universe may not care about us. The cosmos does not assign meaning or purpose, but we care, we assign meaning. We create purpose, and that is enough. Our lives matter because we are here, because we experience joy and sorrow, because we love and create and dream. The universe may be indifferent, but we are not. We are the part of the universe that has become aware of itself. We are matter organized in such a way that it can contemplate its own existence. That is extraordinary, that is precious. The pale blue dot perspective can also be a source of comfort. The problems we face, no matter how overwhelming they seem, are small in the context of the cosmos. The anxieties that keep us awake at night, the failures that haunt us, the conflicts that divide us. All of it is happening on a tiny stage, and that can help us keep things in proportion. It can remind us not to take ourselves too seriously. It can help us let go of petty grievances and focus on what truly matters. What truly matters is that we are here, on this small world, for a brief moment in cosmic time. We have the chance to experience this universe, to see the stars, to learn, to grow, to connect with others, to create something beautiful, to leave the world a little better than we found it. The pale blue dot also reminds us that we are connected to the cosmos. The atoms in our bodies were forged in the cores of ancient stars, the iron in our blood, the calcium in our bones. The oxygen we breathe, all of it was created billions of years ago in stars that lived and died before the sun was born. We are made of stardust, literally. We are the universe experiencing itself. And Earth, that pale blue dot, is the only place we know where this miracle has occurred. The only place where stardust has organized itself into living, thinking beings. That makes Earth special. Not because it is large, not because it is at the center of anything, but because it is home to life, and life, as far as we know, is rare. So yes, Earth is small. Unimaginably small when compared to the scale of the universe, but it is also precious beyond measure. It is the cradle of all we know, the birthplace of consciousness. The only world that has looked back at the cosmos and asked, why? As we near the end of this journey, let us hold this image in our minds, the pale blue dot, suspended in a sunbeam. Alone in the cosmic dark, small, fragile, precious, home, we have journeyed across the cosmos. We have seen the true scale of the universe. And throughout this journey, one question has lingered in the background, a question that becomes more profound the farther we travel. Are we alone? Earth may be small, but it has accomplished something extraordinary. It has produced life, not just simple life, but complex, diverse life, millions of species, each adapted to different environments. From bacteria living miles beneath the ocean floor to birds soaring through the sky, from microscopic organisms to whales weighing hundreds of tons, Earth is teeming with life. And among all this life, one species has developed something even more remarkable: consciousness, self-awareness, the ability to contemplate existence itself. Humans are not the only intelligent animals on Earth. Dolphins, elephants, great apes, and many other species show signs of intelligence and self-awareness, but humans have taken it further. We have developed language, culture, science, art. We have looked up at the stars and asked questions. We have built tools to extend our senses across the cosmos. This raises a profound question. If life arose on Earth, could it arise elsewhere? Given the enormous size of the universe, the billions of galaxies, the trillions of stars, the countless planets, it seems almost certain that life must exist somewhere else. And yet we have found no evidence of it. No signals, no artifacts, no visitors. This puzzle is known as the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked during a lunch conversation in 1950, "Where is everybody?" The paradox is this: the universe is old and vast. Even if intelligent civilizations are rare, there should be many of them scattered across the galaxy. Some should be millions or billions of years older than us. They should have had time to develop advanced technology. They should have spread across the galaxy. They should have left signs of their existence. So why have we not detected them? There are many proposed solutions to the Fermi paradox. Each one is fascinating, and each one has profound implications for humanity's place in the universe. One possibility is that intelligent life is incredibly rare. Maybe the jump from simple life to complex life is extremely difficult. On Earth, life appeared relatively quickly after the planet cooled enough to support it, but complex life took much longer. For about 3 billion years, Earth was inhabited only by single-celled organisms. The leap to multicellular life happened only about 600 million years ago. Maybe that leap is so difficult that it happens only once in billions of planets, or maybe intelligence is rare. Many species on Earth have existed for millions of years without developing human-like intelligence. Maybe the evolutionary pressures that led to human intelligence are unusual. Maybe most planets with life remain forever populated by simple organisms or non-technological animals. Or maybe technological civilizations tend to destroy themselves shortly after developing advanced technology. We have had nuclear weapons for less than a century, and we have already come close to using them in ways that could end our civilization. Maybe every civilization reaches a point where it develops technology powerful enough to destroy itself, and maybe most fail to navigate that dangerous period. Maybe the galaxy is filled with the ruins of civilizations that destroyed themselves. Another possibility is that civilizations exist but choose to remain silent. This is sometimes called the dark forest hypothesis. Maybe broadcasting your presence to the galaxy is dangerous. Maybe there are hostile civilizations out there, and the smart thing to do is hide. Maybe every wise civilization learns to keep quiet, to listen but not speak. If that is true, the galaxy could be full of civilizations, all hiding from each other, all listening in silence. Or perhaps civilizations exist, but communicate in ways we cannot detect. We have been listening for radio signals, assuming that advanced civilizations would use radio for communication. But maybe radio is a primitive technology. Maybe advanced civilizations use quantum communication, or neutrinos, or something we have not even imagined. Maybe they are broadcasting all the time, but we are listening on the wrong frequencies, using the wrong tools. Or maybe civilizations are simply too far apart. Even if there are thousands of intelligent species in the galaxy, the distances between stars are so vast that contact is effectively impossible. A radio signal traveling at the speed of light would take years, decades, or centuries to reach even nearby stars. A reply would take just as long. A conversation would be impossibly slow. Physical travel between stars is even harder. With our current technology, journeys to other stars would take tens of thousands of years. Even with hypothetical future technology, crossing the galaxy would require centuries or millennia. The universe might be filled with civilizations that will never meet because the distances are simply too great. There is another possibility, one that is both humbling and awe-inspiring. Maybe we are the first. Maybe in all the vastness of the galaxy, in all its billions of stars, intelligent life has arisen only here, only now. We might be the universe's first attempt at understanding itself. If that is true, then what happens on Earth takes on cosmic significance. We are not just a species on a small planet. We are the leading edge of complexity in the universe. We are the cosmos becoming aware of itself for the first time. This possibility carries a profound responsibility. If we are the first, then the future of intelligence in the galaxy depends on us. If we survive and spread, we could seed the galaxy with life and consciousness. If we fail, the universe might remain dark and unaware for billions more years, until another species somewhere else evolves to ask the same questions. But perhaps the most unsettling possibility is that we are simply unable to recognize intelligence when we see it. We assume that intelligent life will be like us. That they will build cities, develop technology, send signals, but maybe intelligence takes forms we cannot imagine. Maybe there are beings made of energy, or living in the hearts of stars, or existing in dimensions we cannot perceive. Maybe the universe is full of intelligence, and we are blind to it because we are looking for ourselves. We do not know which of these possibilities is true. We have only one example of life, Earth. Everything living on our planet, from bacteria to blue whales, shares a common ancestor. All life on Earth is related. We all use the same genetic code, the same basic biochemistry. This suggests that life arose once on Earth, and everything living today descended from that original life form, but we do not know how that original life arose. The origin of life is one of the biggest unsolved questions in science. We know that about 4 billion years ago, Earth had liquid water and a variety of chemical compounds. Somehow in that environment, non-living chemicals organized themselves into something that could reproduce and evolve, but the details remain mysterious. We can simulate conditions of the early Earth in laboratories. We can produce amino acids and other building blocks of life, but we have not yet created life from non-living matter. Some scientists think life arises easily wherever conditions are right. In this view, the universe might be teeming with life. Others think life requires an incredibly unlikely series of events. In this view, life might be extraordinarily rare, perhaps unique to Earth. What we do know is this: Earth exists, life exists here, and among that life, consciousness has emerged. We are beings capable of understanding our place in the cosmos. We can measure the distance to stars. We can calculate the age of the universe. We can trace our own origins back to the Big Bang. We are made of atoms forged in ancient stars. We are the universe looking back at itself. This is perhaps the most profound realization of all. Regardless of whether we are alone or one among many, the fact that we exist is remarkable. The fact that matter has organized itself into structures complex enough to contemplate their own existence is extraordinary. Size does not determine significance. Earth may be tiny, but it has produced something that, as far as we know, is unique in all the cosmos, beings capable of wonder. And so, as we near the end of our journey, we return to where we started, to Earth, this small world, this pale blue dot. It may be the only place in the universe where life exists. Or it may be one of countless worlds harboring life. We do not know, but we know it is precious. We know it is fragile. We know it is home. Let us turn now to Earth's future. And to the final thoughts of our journey together, let us look ahead for a moment. What does the future hold for Earth, for us, for this small world that has been our home for so long? In the short term, the next few million years, Earth will remain largely as it is. The continents will continue drifting slowly across the surface, reshaping the geography. The climate will change naturally, cycling through warmer and cooler periods as it has for billions of years. Life will continue evolving, adapting to whatever conditions arise. If humans survive, we will continue to develop, to change, to shape our world and perhaps other worlds. But in the longer term, about 1 billion years from now, the sun will begin to change. As it ages, it will grow gradually hotter. The increased heat will cause Earth's oceans to evaporate. The atmosphere will become thick with water vapor. The greenhouse effect will intensify. Earth's surface will become increasingly inhospitable. Complex life will struggle to survive. Eventually, Earth will become too hot for any life as we know it. In about 5 billion years, the sun will exhaust its hydrogen fuel. It will begin fusing helium in its core. This will cause it to expand into a red giant, growing so large that it will likely engulf Mercury and Venus. Earth might survive on the outer edge of the sun's expanded atmosphere, but it will be a scorched, lifeless rock. All the oceans will be gone. The atmosphere will be stripped away. Everything that once made Earth a living world will be erased. Eventually, the sun will shed its outer layers, creating a beautiful planetary nebula. And at the center will remain a white dwarf, the dense, hot core of the sun, slowly cooling over trillions of years. Earth, if it still exists, will orbit this dim remnant in permanent darkness and cold, but that is billions of years away, an almost incomprehensible span of time. For now, Earth is vibrant, alive, full of beauty and possibility, and there is another future to consider. If humans survive and continue to develop, we might one day leave Earth. We might establish colonies on Mars, on the moons of Jupiter and Saturn, perhaps even in orbit around other stars. If that happens, Earth will remain important as our birthplace, but it will not be our only home. We will become a spacefaring civilization, spread across multiple worlds. Even if we spread throughout the galaxy, even if we inhabit thousands of worlds, the scale of the universe will remain humbling. The Milky Way is just one galaxy among trillions. Human civilization, no matter how far it spreads, will occupy only a tiny fraction of the cosmos. But perhaps that is as it should be. We do not need to fill the universe to matter. We do not need to be large to be significant. What matters is that we are here, that we experience, that we create, that we love, that we wonder. So let us return one final time to where we began. To Earth, this small world beneath your feet, this pale blue dot suspended in a sunbeam, this home to everything we have ever known. Earth is small. We have seen that clearly on this journey. Compared to the sun, Earth is tiny. Compared to Jupiter, it is minuscule. Compared to the Milky Way, it is invisible. Compared to the observable universe, it is beyond measurement. It is smaller than the smallest thing we can imagine when placed against the cosmic scale. And yet, Earth is also extraordinary. It is the only world we know that harbors life. The only place where consciousness has arisen. The only location in all the vastness of space where the universe has become aware of itself. Size is not the same as significance. A single human life is brief, just a few decades in a universe billions of years old. A human body is small, just a few feet tall on a planet thousands of miles across, but a human life still matters. It matters to the person living it. It matters to the people they love. It matters in the moments of joy and connection, in the beauty created, in the kindness shown. The same is true for Earth. It may be small, but it is precious. It is home, and that is enough. As you drift toward sleep tonight, let this perspective settle gently into your mind. You are standing on a small world. A world orbiting an ordinary star, in a galaxy among trillions, in a universe almost beyond comprehension. The scale is vast, the distances are enormous, and Earth is tiny, but you are here. On this world, at this moment, part of an unbroken chain of life stretching back billions of years, made of atoms forged in ancient stars, connected to the cosmos in ways both physical and profound. Your life, brief as it is part of the universe's story. You are one of the ways the cosmos experiences itself, and that is beautiful. So sleep well tonight, knowing that you rest on a small planet in a quiet corner of a vast universe, a universe that is mostly empty, mostly dark, mostly silent. But here on this tiny world there is light, there is warmth, there is life, there is you. The universe is enormous, Earth is tiny, but Earth is also home. And home, no matter how small, is where we belong. Close your eyes now. Let the vastness of space wash over you gently. Let the scale of it all remind you that your worries are small, that your time here is precious, that this moment, right now, is all we truly have. The stars will continue turning overhead. The galaxy will continue its slow rotation. The universe will continue expanding. And here on this pale blue dot you will rest. Good night.